Welcome back to the deep dive. We often talk about these incredibly complex electronic systems, radar, navigation, communications, but really those systems are only as reliable as the tools we use to test them.
That's so true.
Today, we are taking a massive step back from all that high-level theory and strapping in for what is essentially an intensive boot camp.
Yeah, a boot camp in the procedures, the logistics, and the rigorous physics required to keep highly complex test equipment operational and, most importantly, accurate.
Exactly.
That's it. Our deep dive today is designed specifically for you, the person who needs a structured, thorough understanding, a real coaching plan for test equipment administration and use. This knowledge is absolutely foundational.
This is going deep into the official sources.
We are. Primarily NEATS Module 16, Chapter 1, which lays out the entire administrative and operational system.
Okay, let's zoom in on the mission then. Our core goal is to cut through any of the, bureaucratic fog and get straight to the things that matter most.
The numerical data points, the definitions, and the clear cause and effect relationships.
Yes. We need to master the logistics systems like SCLSIS and measure, understand the 8 critical calibration status labels instantly, internalize all the non-negotiable safety procedures, and then finally,
grasp the fundamental precision math behind the electrical bridges used for those high-accuracy component measurements.
It's a journey from the inventory clerk's ledger all the way to the lab bench.
It really is. And if you are preparing for a certification or managing critical assets or just trying to understand how massive organizations maintain electronic readiness, every single detail we cover here is, well, it's mandatory.
All right, so where do we start?
Let's start with the administrative groundwork. This ensures that before a wrench is even picked up, we know exactly what piece of gear we have and where it belongs.
When you're managing test equipment across an entire fleet or a massive enterprise, standardization isn't just a suggestion, right? It's mandatory.
Oh, it's absolutely mandatory for efficiency and budget control. Our source introduces us immediately to the first piece of jargon, JTDS.
JTTDS.
Okay, what's that? It stands for the Joint Electronics Type Designation System. This is the standardized naming convention, the nomenclature, that's currently used by all branches of the military to identify test equipment.
So it creates a common language.
A common language, exactly. It ensures global interoperability and clarity. When you say you need a specific type of signal generator, everyone knows exactly what device you mean, regardless of the manufacturer, whether it's Tektronix, Fluke, or Agilent.
It's like a universal part number that cuts across all the brands.
Precisely. The JETDS provides a unique, standardized identifier that cuts across all those proprietary model numbers.
And that clarity is essential for logistics, but we know things can get out of control. When standardization breaks down, costs just skyrocket.
They do. And that brings us to the history of classification and control. The Electronic Test Equipment Classification Board, or ETE, was established in a pivotal year, 1973.
And why then? What was happening?
The background is pretty telling. Before this, the sheer volume of new electronic equipment flooding into the system, what they called undesirable electronic test equipment, had created an unmanageable inventory and support situation.
I want to zoom in on that term, undesirable. Was the equipment undesirable because it was bad quality, or was it something else?
That's a crucial distinction. It wasn't primarily about quality. It was almost entirely a logistics nightmare.
A nightmare how?
Well, think about it. If 10 different labs ordered 10 different kinds of voltmeters, all capable of the same basic function, the supply chain suddenly needed 10 different sets of spare parts.
10 different maintenance manuals.
10 different training courses. The ETE board was established to control the proliferation of non-standard gear, specifically by creating 2 key classifications to manage what was allowed into the inventory.
So they established general purpose versus special purpose. Let's start with the workhorse.
That would be GPT, General Purpose Electronic Test Equipment. This is your flexible, versatile workhorse. This equipment has the capability, without any modification, to generate, modify, or measure a range of electronic functions needed to test 2 or more systems of basically different design.
Like a standard oscilloscope or a good digital multimeter.
Exactly. Those are the definition of GP. They're designed to be universally applicable.
And then on the other side, you have the tooling that is hyper-specific.
That's SPEET, Special Purpose Electronic Test Equipment. This gear is designed specifically to generate, modify, or measure electronic functions of a specific or peculiar nature required to test a single system or equipment.
So like a custom piece of gear to test one particular missile guidance system.
Perfect example. It has one job, and no other equipment can effectively do it.
So the core cause and effect relationship here is that this uncontrolled, non-standard GP led directly to inventory control nightmares and dramatically increased support costs.
That's it. The ETE classification board had to step in. They specifically evaluated whether a proposed piece of non-standard GPT should be approved or disapproved. They were looking for overlap and redundancy.
And by limiting the variation, they limited the training, the manuals, the part.
Everything. Standardization is efficiency. This 1973 decision was a massive administrative pivot aimed at saving billions in long-term support costs.
Got it. So the takeaway is pretty clear. If it tests multiple different systems, it's GPT. If it tests only one specific system, it's SPETE.
Precisely. And JGTDS gives it a uniform name.
Okay, let's do a quick recap. Section 1.1 summary.
Yeah.
JGTDS provides the standardized naming. The ETE board was created in '73 to manage costs by classifying equipment. AGP is the versatile tool, SPETE is the custom tool. And the whole point was to stop the flood of redundant gear.
You've got it.
So now that we know what the equipment is called, we need to know where it is and what its condition is. This is where we get into the first major logistics tracking system.
Yes, the program designed to keep tabs on every single asset, that is SCLSS.
SCLSS. Okay, another jargon term.
It stands for the Ship Configuration and Logistics Support Information System. As the name suggests, it tracks logistics and configuration. Its whole purpose is to keep tabs on all installed and portable equipment across the entire fleet.
So it's monitoring its existence, its current location, and all the changes made to that equipment.
Exactly. And this isn't a static database. For the SCLS program to function effectively, it requires two basic mandatory elements.
Which are?
The first is validation. This is the initial heavy lift establishing the accurate baseline of data. It means walking the deck plates, verifying serial numbers, and ensuring the initial inventory is 100% accurate.
You can't manage what you haven't counted.
You can't. And the second element is where the real effort comes in. Inventory updating.
Which means correcting errors, but also documenting every single change.
Every single one. If you swap out a component, move a portable tester from one compartment to another, or retire a piece of gear, the record must reflect that change immediately.
I have to ask, in a fast-moving environment, like on a ship that's deploying, how difficult is it to keep up with that? Doesn't that create a huge administrative burden?
It absolutely creates a burden, but it's a necessary one. The moment SCLSI's records become inaccurate, the entire support infrastructure just collapses.
So if the system thinks you have one type of calibration standard when you actually have another,
your replenishment order will fail. That's why the mandate is so rigorous. The accuracy of that data directly impacts operational readiness. The system has to be dynamic.
And accurate records are necessary because they dictate what comes next. Maintenance. So we have two distinct categories of maintenance activity.
We do. First, we have preventative maintenance, or PM. This is the routine, proactive work designed to catch problems before they cause a failure.
So things like visual inspections of cabling, making sure connectors are clean, proper lubrication.
All of that. PM determines whether equipment is operating properly and prevents future catastrophic failures.
Then, after a failure, we enter the reactive phase.
Corrective maintenance, or CM. This is what happens when something breaks. It involves isolating the equipment troubles, a process we call troubleshooting, and then repairing the equipment to restore its proper performance. This is the fix-it phase.
Let's nail the definition of troubleshooting because it's a mindset as much as it is a procedure.
It really is. It is officially described as a logical and systematic approach to evaluating equipment performance. The technician compares the equipment's actual operation with the way it should be operating.
Based on the manuals or known specs.
Exactly. And the key here is that this process actively avoids the inefficient hit or miss or the dreaded Easter egging methods where you're just randomly swapping components hoping to get lucky.
That just wastes time, money, and parts.
Immense amounts. A logical diagnosis saves time.
Okay, quick recap too.
Okay.
SCLS tracks where equipment is through validation, the baseline, and inventory updating the ongoing changes. Maintenance is split into PM, which is proactive, and CM, which is reactive troubleshooting and repair.
Yeah.
And that troubleshooting must always be systematic.
Perfect.
All right, we're moving from the logistics of asset tracking to the quality control that dictates whether that asset is actually fit to be used. This all hinges on accuracy, which brings us to calibration.
And this is a fundamental distinction we have to clarify because these terms are often used interchangeably, but they are completely different activities.
Calibration versus repair.
Yes. The crucial definition here is that calibration is Well, little more than checking, adjusting, or systematically aligning a test instrument to a known standard. It's an adjustment process.
So calibration is fundamentally about accuracy and adjustment, whereas repair is entirely physical.
Right. Repair work deals with fixing physical damage, replacing a blown fuse, repairing a frayed power cord, swapping a broken meter, replacing a burned out component. It restores the physical integrity of the instrument.
And the sequence matters. If an instrument is physically damaged, it has to be repaired before it can be calibrated.
Absolutely. Calibration ensures accuracy after the physical integrity is restored. You can't verify the accuracy of something that doesn't even turn on.
The ultimate result of this quality control process is communicated instantly, right on the equipment itself, via these physical tags.
All governed by the Met-Cal Metrology Calibration Program. And for anyone operational, recognizing these 8 principal labels is absolutely critical for safety and mission readiness.
So let's go through the key ones, prioritizing the color and what it tells you to do.
We start with the gold standard, the one you want to see, calibrated. This has black lettering on a white background.
It
means the instrument has been tested, adjusted, and is within its applicable tolerance on all parameters. You can pick it up and use it with full confidence.
Okay. Now, let's look at the first red flag, one that demands immediate attention. Calibrated referred to report. This one uses red lettering on a white background.
This is where the nuance comes in. It tells the user that the instrument is usable, but the actual measurement values must be known to use it effectively.
So it's out of tolerance, but in a predictable way.
Exactly. It's out of tolerance, but the offset is stable. So if you need to make a reading of 10 volts, and the report says the instrument reads 10.1 volts when the standard is 10 volts, you have to apply that compensation. You must consult the paperwork before use.
That sounds like an increased risk. Why would we ever use a refer to report instrument instead of just a calibrated one?
It's often a trade-off. It could be dictated by operational tempo or component complexity. If an instrument is really difficult to calibrate perfectly, or if the out-of-tolerance reading is stable and minimal, it can be kept in use with compensation.
It keeps essential gear available.
It does, provided the user exercises that heightened vigilance and records the compensation.
Moving to the specialized warnings. Special calibration. Black lettering on a yellow background. What triggers this tag?
It's used when some unusual or unique condition in the calibration needs to be drawn to the user's attention. The source provides a critical example: multiple calibration intervals.
Okay, what does that mean?
Imagine a complex test set where the main chassis only needs calibration every 12 months, but a specific internal component, like a high-frequency attenuator, requires calibration every 4 months. The yellow tag alerts you to that partial, more frequent requirement.
And if you ignore it, you risk using an uncalibrated component inside an otherwise calibrated box.
Precisely.
Next, we have the tags that shift responsibility. User calibration. This is black on white, but it's affixed by the user, not the tropical lab.
This means the user is responsible for performing the calibration procedures themselves, often using local standards. This applies to things like hardness testers. The calibration interval use, daily, weekly, is specified for that equipment in the metrology requirements list, the MET-TRL.
Now let's talk about pausing the cycle. Inactive calibrate before use. Green lettering on a white background.
This tag is an administrative tool. It's for equipment that's not currently being used, allowing the recalibration date to be postponed. It reduces the burden on the Met-TAL system.
But the operational consequence is absolute.
It is. The instrument cannot be used for any purpose until it is officially recalled, tested, and certified as calibrated. It is essentially locked down.
Then the permanent exemption. Calibration not required. Orange on a white background.
This status is granted under 3 specific criteria. 1, the instrument doesn't make quantitative measurements like a simple continuity light. 2, the device is fail-safe. Or 3, its performance relies entirely on external, already calibrated sources.
The definitive failure. Rejected, refer to attached tag. The universal stop sign. Black lettering on a red background.
This is the definitive statement of failure. It means the instrument failed acceptance criteria during calibration and can't be adequately repaired. The operational mandate, pull it from service immediately. It is a liability.
And finally, the security tag. Calibration void if seal broken. Simple black on white.
This label is placed over readily accessible user adjustments that could affect calibration. It's purely preventative to stop unauthorized tampering. It's not used over normal operator controls.
Okay, recap number 3. Calibration is adjustment. Repair is physical fixing. The tags dictate operational status. If you see red on white, you must read the report for compensation. If you see black on red, it is a definitive failure and must not be used.
Exactly.
We've established the standards, tracked the location, and verified the status. Now, how do we mobilize all this test equipment and ensure it gets serviced on time?
This requires a dedicated scheduling system.
Enter the second major logistics system, Measure.
Yes, Measure is the metrology automated system for uniform recall and reporting. This is a data processing system designed to standardize the recall and scheduling of all test, measurement, and diagnostic equipment (TMDE) into calibration facilities. It eliminates human error.
And the data input for this system is centralized on one key piece of physical documentation.
That's the meter card, the metrology equipment recall and reporting card. This is the physical record of all calibration activity for a specific piece of gear. The accuracy of the meter card is vital as it feeds the Measure system its scheduling data.
And based on that data, Measure automatically produces specific recall schedules.
It does. Two key formats. First, Format 310, the general test equipment inventory, is produced monthly. Second, and more critical for managers, is Format 804, the specific recall schedule for on-site equipment. This is generated monthly or quarterly and lists exactly which pieces of TMDE are coming due.
So the whole system is built to prevent gear from falling out of the calibration cycle.
That's the goal.
Now, let's discuss an interesting administrative policy that impacts this flow. The no reject policy at intermediate maintenance activities, or IMAs.
This policy is a crucial mandate designed to maximize uptime. It states that equipment submitted for calibration will be repaired if it's found to be inoperative. This holds true even if the equipment was previously marked rejected.
That sounds great for readiness, but doesn't it incentivize just pushing through minimal repairs to clear the queue? A kind of Band-Aid fix.
That's a fair concern, and it's why the system needs rigorous follow-up reporting via the meter card. The no-reject policy is rooted in the fact that essential test equipment can't afford administrative delays. The policy mandates that an inoperative asset submitted for calibration cannot simply be returned untouched. It must be fixed.
So it streamlines the repair procedure and cuts down on delays.
Significantly, the emphasis is on getting the equipment functional and accurate as quickly as possible.
Okay, recap 4. Measure is the brain, standardizing recall via the meter card data, generating monthly schedules like Format 804. The no-reject policy at IMAs ensures equipment gets repaired first, maintaining operational readiness.
You got it.
We've covered the logistics and the administration. Now we move into the actual environment where the work is done, where people interact directly with precision instruments and energized circuits.
Yes, we need to focus on protecting the instruments and, more importantly, protecting the personnel.
So let's start with instrument protection.
Right. Test instruments are precision tools. They are delicate. The source lists 3 primary hazards that can cause immediate, irreversible damage.
Number 1 is mechanical shock.
This is the simple act of rough handling, dropping it, or exposing it to heavy vibration. The internal components, specifically the permanent magnets and the delicate moving coil meters, are highly sensitive.
And the cause and effect is simple. You drop a meter, you can permanently throw off its calibration.
Exactly. Number 2, exposure to strong magnetic fields.
So don't store your test gear next to a giant motor.
Right. Strong external fields will permanently impair the accuracy of instruments with permanent magnets. It's a long-term degradation issue.
And the third, and probably the most common error in the field, excessive current flow, overloading the instrument.
This is a critical point that demands meticulous procedure. Too much current, even for a moment, can burn out internal components. The single most vital precaution here is always use the maximum range scale first.
You only shift down after you've verified it's safe.
Only after. If you start on the wrong scale, the surge can instantly destroy the meter.
The sources also list some other key precautions, particularly with inductive components.
Yes. For instance, current transformers, or CTs. Never open the secondary of a CT when the primary is energized. It creates an extremely high, dangerous voltage spike.
And for potential transformers or PTs.
You must never short-circuit the secondaries when the primary is energized. That leads to excessive, damaging current flow.
And here is the essential misconception alert we need to reinforce. Never attempt to measure the internal resistance of a meter movement with an ohmmeter.
That's right. It seems logical, but the current from the ohmmeter's own battery is often enough to damage the delicate moving coil movement. You have to use specialized methods.
All right, recap number 5. Protect instruments from dropping, strong magnets, and especially overloading. Always start measurements on the highest range, and don't use an ohmmeter to check a meter's internal resistance.
Got it.
Instrument safety is a cost consideration. Personnel safety is a life-or-death mandate.
Absolutely. And the cardinal rule of electronics maintenance, which must always be the first thought, is explicit. If at all possible, do not undertake repair work on energized circuits. De-energize and log out, tag out first.
But if it is absolutely necessary, there's a strict, non-negotiable checklist that must be followed.
The first rule of this checklist is about immediate emergency response. You must do not work alone. You have to station an assistant near the main switch or circuit breaker, ready to de-energize the equipment instantly.
And that assistant has to be qualified in first aid for electrical shock.
They do, and they must be standing by the entire time.
You also have to ensure that the path to ground is broken.
You must be insulated from ground. That means an approved rubber mat or layers of dry canvas or wood. This prevents your body from becoming part of a complete circuit between the energized component and Earth.
Now let's discuss the famous, seemingly primitive but effective one-hand rule.
When practical, you must use only one hand when working on the circuit, keeping the other behind you or in your pocket.
Why is that so important?
It's designed to prevent current from crossing your chest. If current flows from one arm to the other, it crosses the heart, which dramatically increases the risk of fatal ventricular fibrillation. By using only one hand, the current path is restricted to one limb.
It significantly increases your chance of survival. Now let's look at specific numerical voltage requirements. These are non-negotiable mandates.
2 critical thresholds. The first is, if the voltage exceeds 150 volts, you are explicitly required to wear rubber gloves.
Why specifically 150 volts? Is there a physiological reason for that cutoff?
Below 150 volts, standard insulation materials and skin resistance are generally sufficient. But once you cross 150 volts, the potential is high enough that even slight moisture or compromised insulation dramatically increases the chance of lethal current flow. The gloves provide that necessary high-resistance barrier.
Furthermore, you must eliminate anything that could become a conductive path on your person.
Yes. No loose clothing, no metal on shoes, no rings, watches, bracelets, or metal fasteners like zippers. These items create potential short circuits or conductive paths straight through your body.
Okay, the highest danger scenario is high voltage, specifically circuits exceeding 300 volts. The safety procedure here is mandatory and must be followed step by step.
This is the rigorous 7-step shutdown discharge measure sequence. It's in place because high-capacitance circuits, like in radar power supplies, can retain a lethal charge for hours or even days after power is removed.
Let's detail that mandatory sequence.
1. Turn off the equipment power. 2. Immediately short circuit or ground the terminals of all components capable of retaining a charge, especially capacitors. 3. Connect your meter leads to the points you intend to measure.
Then you turn the power on.
4. Turn on power, observe the reading. 5. Turn off power. 6. You must short circuit and ground all components again. 7. Finally, disconnect the meter leads.
You're cycling the power just for one quick reading and discharging the lethal components twice around every measurement.
You have to. And when we discuss the danger of shock, the source is clear. Current determines the intensity of an electrical shock.
Voltage is the potential, but current is the actual killer.
Yes. A low voltage can be lethal if resistance is low and current is high. A very high voltage might be harmless if the current is minimal, like with static electricity, but the focus is always on controlling the current path.
Recap 6. Working energized is extremely hazardous. Over 150 volts requires rubber gloves. Use one hand, stay insulated. And for high voltages over 300 volts, follow that strict shutdown, discharge, measure, discharge sequence.
Absolutely.
Since we stress the danger of residual charge, we need to specifically discuss the tool used for safe discharge.
The safety shorting probe. This is an approved, specialized tool used to safely discharge capacitors and cathode ray tubes individually after disconnecting the power source.
And the procedure for using it is mandatory.
It is. You must always assume there is voltage. You start by connecting the probe to a good ground, and this is critical. Scrape off any paint to ensure a solid, low-resistance ground path.
Connect the ground clamp first, then proceed to the component.
Yes. Hold the probe only by the insulated handle and touch the exposed hot terminal. Hold it there for several seconds to safely bleed the retained charge to ground.
What about working on de-energized circuits? We still need rules to prevent accidental re-energization.
Correct. The circuit must be de-energized, and all circuit breakers and switches must be secured locked, if possible, in the open or off-F position, and they must be clearly marked with a danger tag.
Lockout, tagout.
The official procedure. It ensures no one mistakenly cycles the power while you're working.
Finally, let's confirm the integrity of grounding systems for portable power tools.
There's a critical numerical requirement here. A meter must be used to ensure the ground pin from the tool chassis back to the equipment ground has a resistance of less than 1 ohm.
Less than 1 ohm. That's an incredibly low resistance. Why so tight?
Because in the event of a chassis fault where a live wire touches the metal casing, the fault current needs the absolute path of least resistance to ground to trip the breaker instantly. If the resistance is higher than 1 ohm, the casing could remain energized long enough to cause a severe shock.
Okay. With admin and safety locked down, we can move into the actual measurement of the basic electrical quantities, V, I, R, C, and L. This is the core skill for any troubleshooter.
It is. And voltage measurement is your most valuable diagnostic tool. It's what you use to quickly locate a fault in a circuit by taking point-to-point measurements. It answers the question, is the correct potential present here?
And we've said it before, but the primary precaution for voltmeter use is foundational.
Always set the voltmeter to the highest range before measuring. You dial down only once you've confirmed it's safe.
Now, a critical concept about voltmeters is their sensitivity.
Yes, voltmeter sensitivity is listed on voltage charts, and it's measured in ohms per volt. It's a direct indicator of the internal resistance of the meter. A high ohms per volt rating means a very high internal resistance.
And why does that matter?
Because a good voltmeter should act like a perfect open circuit. It should measure the voltage without changing the conditions it's measuring. This concept of sensitivity sets up our final thought for the day regarding circuit loading.
We'll come back to that. What about current measurement using ammeters?
That operates fundamentally differently. Voltmeters are connected in parallel. Ammeters must become an actual part of the circuit. The crucial rule is that ammeters must be connected in series with the circuit under test.
Which means you usually have to interrupt or open the circuit to insert the ammeter.
Exactly. And because that can be tedious or dangerous, the standard procedure is often to calculate the current using Ohm's law instead, by measuring the voltage across a known resistance.
Okay, recap 7. Voltage is measured highest range first and is point-to-point. Current requires an ammeter placed in series, interrupting the circuit. And voltmeter sensitivity in ohms per volt should be high to avoid loading the circuit.
Got it.
Now for resistance, capacitance, and inductance.
Resistance measurements are used routinely in corrective maintenance, mostly for troubleshooting opens or shorts. But just like current, they come with an absolute safety requirement.
The ohmmeter precaution.
Non-negotiable. The circuit being tested must be completely de-energized before you use an ohmmeter.
Because the ohmmeter uses its own internal battery to send a current through the component.
And if there is any external voltage applied, you risk damaging the ohmmeter itself. You also have to remove any delicate components, like transistors, that might be damaged by the ohmmeter's current.
Switching gears to capacitance. A key concept here isn't just the value, but the quality of the component.
Right, which is measured by its loss factor. This is called the power factor. It's an indication of the various losses of a capacitor. A perfect capacitor stores energy without loss. A real one has leakage.
In practical terms, what does a bad power factor indicate?
It means the dielectric material itself is breaking down. It's leaking excessive current, acting more like a resistor and less like a storage device. It needs to be rejected.
And finally, inductance measurement.
Inductance measurements are seldom required in routine troubleshooting, but they are incredibly useful for finding the unknown inductance value of unmarked coils or transformers. It's a niche measurement, but essential for failure analysis.
Okay, now we make the jump from routine handheld measurements to the realm of high precision. If you need laboratory-grade accuracy for RC or L, you use bridge circuits.
Bridges are composite circuits that operate on the principle of a balanced circuit. The goal is to adjust known components until a detector meter reads minimum or zero.
The grandfather of these circuits, the DC standard, is the Wheatstone bridge.
It is, and it's used exclusively for the precise measurement of unknown resistance, or R sub X.
How does it work?
It uses 4 resistors in a diamond shape, powered by a DC battery. 3 resistors are known, and the 4th is the unknown. The principle relies on creating a scenario where the voltage drop across one arm exactly equals the drop across its adjacent arm.
So when the drops are equal, what happens in the middle?
That's the balance condition. When the bridge is properly balanced, the galvanometer, the detector meter in the center, reads precisely 0. Zero deflection means there is no difference in potential between the two measurement points. No current flows through the meter.
And that zero reading allows us to equate the ratios of the arms.
Exactly. When you do the math, it yields the crucial balance formula. The unknown resistance, R sub x, equals R2 times R3, all divided by R1.
Let's run the numerical example from the source to make that tangible. If R1 is 60 ohms, R2 is 100 ohms, and R3 is 200 ohms.
We plug those values in. R sub x equals 100 times 200 divided by 60. That's 20,000 divided by 60.
Which gives us a precise measurement of 333.33 ohms, and the accuracy is determined by the precision of those known resistors.
The Wheatstone bridge remains the DC standard for high accuracy resistance measurement.
Recap 8. Ohmmeters need a de-energized circuit. For precision, use bridges. The Wheatstone bridge uses DC voltage and a zero galvanometer reading to calculate unknown resistance using that derived ratio formula. So when we move to measuring reactive components, capacitance, and inductance, we have to shift from the DC-powered Wheatstone to AC bridges.
Right. We can't use DC because capacitors act as open circuits and inductors act as shorts. So instead of a battery, we use an AC signal generator. And instead of a galvanometer, we use an AC meter, often headphones or a detector, and we adjust for a minimum or null deflection.
Let's start with the capacitance bridge. The calculation here is fundamentally different than for resistance.
It is. The key relationship is that current varies inversely with capacitive reactance. This means the ratio expression has to be inverted compared to the resistance bridge formula.
So while for resistance R sub x was proportional to R2 over R1, the capacitance formula flips that.
Correct. The formula for the unknown capacitance C sub x equals R1 times the standard capacitance C sub s, all divided by R2. Notice R1 is on top now.
Let's run the numerical example. If R1 is 20 ohms, R2 is 40 ohms, and the standard capacitance C sub s is 10 microfarads.
We calculate C sub x as 20 times 10 microfarads divided by 40. That's 200 divided by 40.
Resulting in C sub x equals 5 microfarads. The inverse ratio is the key difference.
And the underlying physical reason is that an increase in capacitance actually results in a decrease in opposition to current flow. So the unknown capacitance has to be inversely related to the resistance ratios to achieve balance.
Finally, the inductance bridge. This one is structured similarly to the resistance bridge.
It is. The ratio arms are directly proportional to the unknown inductance. The formula for L sub x is R2 times the standard inductance L sub s, all divided by R1.
And let's run the final numerical example. If R1 is 20 ohms, R2 is 40 ohms, and the standard inductance L sub s is 10 millihenries.
We multiply 40 by 10 millihenries and divide by 20. That is 400 divided by 20.
Which gives us L sub x equals 20 millihenries.
The essential takeaway is recognizing which components' physical properties necessitate that inverted formula capacitance and which use the direct ratio of formula resistance and inductance. Mastering that math allows you to verify components with high precision.
Okay, our final recap, number 9. AC bridges find C and L. The capacitance bridge uses an inverse ratio formula. The inductance bridge uses a direct ratio formula. The mathematics is crucial for calculating unknown component values accurately.
The bridge circuits are the core of precision measurement.
We truly completed an intensive deep dive today, starting with high-level logistics and ending at the mathematical core of precision measurement. We covered the systems that standardize the names, JGDS, and track the location, SCLSIS.
And we mastered the quality control mechanisms, the 8 critical calibration tags under METSAL, which instantly dictate operational status, whether that's a direct use for calibrated, a use with caution for refer to report, or a definitive do not use for rejected.
We also detailed how Measure ensures timely recall using the meter card, backed by that no reject repair policy at IMAS.
And most importantly, we locked down the safety protocols.
Yes. Working energized is extremely hazardous.
No.
But if necessary, we know the mandatory checklist. Station an assistant, stay insulated, use only one hand, wear rubber gloves above 150 volts, and follow that strict 7-step shutdown discharge measure sequence above 300 volts.
Because current is the determining factor in fatal shock. Finally, we established the mathematical core of high-precision testing. The DC Wheatstone bridge uses the condition of zero potential difference to calculate unknown resistance. And the AC bridges allow us to calculate capacitance and inductance, understanding that capacitance requires that inverse ratio calculation.
So here is a final thought for you to chew on. Building on the concept of measurement accuracy we discussed with voltmeter sensitivity, we define sensitivity as ohms per volt, which is the internal resistance of the meter.
Right.
If you were attempting to measure the voltage across a very high resistance circuit, let's say a critical component in a sensor array that has an impedance of several hundred kiloohms, what might be the practical consequence of using a meter with low sensitivity, a meter with low internal resistance on that circuit? Think about how the meter itself might change the voltage it is trying to measure by offering a new, easier path for current. This is the concept of circuit loading, and recognizing when your test gear is lying to you because it is interfering with the circuit is what separates a technician who gets a reading from one who gets an accurate, meaningful reading.
Something to ponder as you apply all this critical administrative and technical knowledge.
Absolutely. Thank you for joining us for the deep dive. We'll talk soon.